Hey, good morning, everybody. Hey, welcome to another video on Papalin Physics Classroom. Okay, today we will be going through the prelim paper by Nanqiao High School. Okay, it's a paper that I gave to my students to practice. If you need the paper, okay, it's in my Google Drive. The link is in my description panel below. Okay, you can go in and download the paper and give it a try. It's a good paper. It has a lot of interesting ideas of testing a certain concept, which I believe is one of the problem that we have as students. Let's say I can only I'm actually good at doing the questions using a certain approach, and sometimes because I'm so good at doing that approach, I tend to miss out the idea that the question can be solved using another method or another approach. So it's actually good to be exposed to different way of solving or different ways of interpreting the questions, okay, to actually open up your exposure to the same concept question. Okay, without further delay, okay, we will look at the paper one for that particular question. Okay, so if you have the paper already, you might want to take out. Okay, and this is the paper one question, and the paper one answer. Okay, if you want to do a short marking, you can pause the video here and actually look at answer for your paper one. Okay, to check which questions you need. You made a mistake. Then after that, if you need the explanation for that particular question, you scroll to the correct the necessary timing for that particular question. Okay, because this video is going to be a long video, so there's no point to look at from the beginning to the end. Okay, if you don't need that particular question. Okay, so you might want to pause the video now here. Okay, so you have done it. Okay, so we'll proceed to the first questions. Okay. Okay, question one here is about prefixes. Okay, it's about I would say it's our ability to do a simple estimations to look at how big the thing is or how small the thing is. Okay, so diameter, the width of the hair and the diameter of the earth. Okay, I would say these are some of the common knowledge that we have about stuff regarding their sizes. So it's good to know how big is actually the diameter of the earth, or actually how big is actually 10 megameter or 10 gigameter, or even how small is a micro or millimeter. Okay, for question two is kinematics. The question revolve around simple constant speed question. Okay, these particular questions talk about constant speed, moving at constant speed of 30 meter per second. After that, it takes 30 meter per second. After it takes 2.4 seconds to pass through a particular the child. So if you look at the particular question and you draw the speed time graph for the situation, okay, you'll find that because it's a constant speed, it will be a simple straight line. Okay, simple horizontal straight line, and it takes 2.4 seconds to actually pass the kid. So this will be the time. So if I want to know the length of the train or the distance traveled, okay, all I need to do for kinematics is actually to look at it at the distance, the area under the graph, which is the distance here. So the distance here, it will be, okay, the area of the triangle. Okay, it will be 30, which is the length, okay, which is the breadth, height, sorry, times the length, which is 2.4. And after that, the distance here will give you will be 72 meter actually. Okay, now the solving technique we have for kinematics, always remember, is that we will be always looking at the two main aspect of velocity time graph, which is the area under the graph, which give us the distance. And sometimes we also want to look at the gradient of the velocity time graph. Why? Because the gradient of velocity time graph actually tells us information like what acceleration. Okay, so if I need to find the accelerations of the object using a speed time graph, I actually look at it in terms of the gradient. Okay, if I want to find the distance travel, I actually look at the area under the graph, which brings us to the important fact that for kinematics, the approach that we have at O level here is that for kinematics, we actually look at the use of the velocity time graph, okay, rather than using the formula itself. Okay. So take note of the approach and how the question is actually crafted to use that particular technique. Okay. Okay, then the next question we have in question three, right, is I would say it's a bit, I would say it's on forces. Okay, so the forces here, some of the common clue that we always use will be the use of constant speed. Okay, when you say constant speed, one of the good things that we always like is that what does it mean? Okay, the constant speed here refer to acceleration of the object is actually 0 meter per second square. Okay, so 0 meter per second square, it means that it's actually a horizontal straight line, like what we see in question 2, horizontal straight line. But indirectly, he also means that if you look at it in terms of Newton's equation, F net equal to ma. Okay, if acceleration is 0, you imply that the right side of these equations is actually a 0. Okay, so which means the left side F net, the sum of all forces, okay, it should actually amount to 0. Okay, so let's look at the forces that is applied, that is experienced by the balloon now. So we have the weight of the balloon, and we will also have the upward force, or what we call it, maybe is the resistance of the balloon when it's rising up. Okay, so here we have the balloon, okay, which is the weight is 800 Newton. Okay, then after that you have an upward force, okay, which is upwards. Okay, and these are the two forces that act on the object itself. So if you look at the net force, okay, it will be a sum of forces, the upward force and the weight of the object itself. So since they are in opposite direction, so it will be a negative sign with difference of the forces. So if you look at algebra, okay, it will be eventually the forces that we are looking for, it will be equal to the weight of the balloon itself, which is 800 Newton. Okay, so the mathematics approach that we use when we solve Newton's law is actually start off from the most important or the most common clue that we given in the question, which is constant speed. Okay, constant speed will lead us to the fact that it's 0 acceleration. And after that, if we use the Newton's law, F net equal to ma, you'll find that it will help us to derive that the upward force is actually equal to the weight itself, whereby the two forces are balanced. Okay, the two forces are of the same magnitude but opposite in direction. Okay, then after that, you will have the answer, which is 800 Newton. Question 4, I would not dwell too much. Question 4 is I would say it's a straightforward question whereby you just utilize the formula density is mass over volume. Okay, the only, I would say the hidden agenda for this particular question is that maybe the cube of size 4 or 3 cm, okay, maybe it will require the students to find the volume of the cuboid, which is, I would say, quite straightforward. Okay, so once you have the volume, which is what, 3 times 3 times 3, okay, because it's a cube, so all sides are the same, followed by the mass of the object, which is 7.2 gram. Okay, you use your calculator and you will get the answer that's given. Okay, so I would say it's a straightforward answer. Okay, here one thing to take note is that the basic shape for volume, I would say it's good to know the basic formula for rectangle, cuboids, okay, and even sphere. Okay, for third pi r cube. Maybe if I need, okay, maybe sphere will come out. Okay, so these are the formulas, common formula that you might want to take note as a student. Okay, the volume of a cuboid, rectangular object, or even a cylindrical shape, or even a sphere, which is a sphere, which is 4 pi r cube. Okay, so these are the common formula, mathematical formula that you might want to take note. Then after that, we look at question 4. Question 4, we look at the way of measuring to get an accurate answer. Okay, if I want to get accuracy of the measurement, okay, measurement, definitely I have to ensure that the cylinder is vertical. So because I am actually I need the vertical height of the measuring cylinder because I want to measure the exact volume. So the water has to be upright, the cylinder has to be upright so that I get the correct reading. So this is definitely one of the important rules that I have to obey. Eye level, definitely, okay. Read the object, the surface at eye level. Why? Because I want to read where the meniscus is to make sure it's actually at the correct position. So what we usually do in the lab, we always tell students to actually put the cylinder on the table and after that lower your body down, rather than lifting up the cylinder to your eye level, which is very, very inaccurate. Then after that, meniscus, water meniscus, remember, is not at the top. Meniscus for water is always at the bottom. So if I want to read the correct level, I will read at the meniscus level. And where's the meniscus? It's always at the bottom level of the meniscus. Okay, so if you look at the cylinder, right, the water level, it actually will have a downward slope here. This is what we call the meniscus. Okay, the surface of the top surface of the water or the liquid. So if you want to read the correct reading, it should be read at the bottom of the meniscus here. Okay, not the top, not the top. Okay, not the top here. Okay, so the correct placement of I should be at the bottom of the meniscus. Okay, after that, of course, I want to use a smaller. I would say I would want to use the most suitable measuring cylinder, and I want to use I would say just the right size. Okay, not too big, not too small. Okay, I want it to be just nice, not too big, because why? The right size of measuring cylinder will actually give me the most accurate measurements. So if I have a small amount of water but I use a large cylinder, so the accuracy level of that measurement will actually be inaccurate. So because I'm actually using the measurement would be maybe too widely spaced. I can't even read the details of the particular water level, because why? The water level is 2 liter. Okay, the amount of water is 2 liter. So getting a big cylinder to measure a small amount of cylinder is actually not accurate. So ideally, I should actually use a cylinder that fits just nice. Okay, so A, B, D are what I want to do to get an accurate reading. So if I would not do to improve based on the question, the answer will be C. Okay, I should not read the top of the meniscus. I should be at the bottom of the meniscus. Question 6, conduction. I would say it's a conduction question. Copper rod. Okay, copper rod is definitely medium. Medium usually look at heating. If you look at medium for heating, it's actually looking at conduction. And conduction, there's always two modes: the molecular vibration and the free electron diffusion. Okay, so these are the common things that we have, are the two methods that we have for conduction. Okay, and the free electron diffusion. Okay, these are two methods. And of course, as students, you need to know that for conduction, especially if it's metal, okay, this method, free electron diffusion, is actually our most important. It's one of the essential mode of transfer, okay, via conduction. Okay, how does the heat transfer occur in copper? Okay, heat copper, basically you have what we call your free electron diffusion inside copper. Okay, your free electron diffusion inside copper, that will be one of the main method here. So definitely I would want to narrow down on free electrons. Okay, and it's always from where? From hot to cold. Okay, from heat transfer is always from hot to cold, and hot means the kinetic energy of the particle is actually more vibrant, much higher than the colder end. So the electrons will actually move from a region, a hot region, to a cold region, and primarily hot region will actually be represented by molecules with high kinetic energy. Okay, moving from the hotter end to the colder end. Okay, remember heat transfer is always from hot to cold. Okay, so that's why automatically I will choose my answer to be D. Okay, I will not choose copper atom. I will not choose copper atom here. Okay, because why? Because for conduction, because the question did mention is called copper, which is a metal, which is why the main method for metal is actually free electron diffusion rather than molecular vibration. But molecular vibration does happen in metal. But just it take I would say the secondary stand. We take a back stand. The main mode of heat transfer in metal will still be a free electron. So between B and D, okay, I will choose D, because D will be the main mode of transfer, the primary method of conduction. So D will be a more accurate answer compared to B. Okay. Now, for question 7, when liquid boils, some molecule escape from it. Where do the molecule escape? Okay, keyword here we look at is boil. Boil will imply from liquid to gas. Okay, so there's a change in state from liquid to gas. Okay, and when we look at liquid to gas, boil, one of the important characteristic that we have to take note is it always occur at what we call your boiling temperature. Okay, and this boiling temperature is otherwise known as, actually, is a particular temperature, or it will remain constant, okay, for a certain amount of time while I'm boiling. So the temperature of the liquid at that phase, at that moment in time when I'm doing boiling, is actually unchanged. Okay, so if you look at the option straight away, you know, there's only option B that remain unchanged. So B will actually be the answer. Okay, and in fact, okay, for boiling, it actually, one of the main characteristic of boiling is actually occur throughout the liquid. Okay, occurring at surface. Okay, if you look at surfaces, okay, this is what we call evaporation. Evaporation only occur at the surfaces. Okay, so it depends on which mode the question is talking about, whether it's boiling or evaporation. You have to know what are the characteristics of the energy, internal energy of the particle. Okay, question 8. The letter, what I call laterally inverted, I would say it's quite a simple question. In fact, I think it's really a safety net question, because this question is actually, I would say, primary school level. Okay, so, but it's an interesting concept to test about electrically inverted. Okay, so take note of this question. Question 9, water wave. Okay, it's a transverse wave. Okay, we talk about reflection and we talk about refraction. Okay, refraction usually occur. Okay, what happened to the speed? What happened to the speed? What happened to the wavelength? What happened to the frequency? Okay, so these are some of the questions that they usually will ask. Okay, so we talk about reflection, water wave being bounced back. Okay, being reflected back. Okay, when the water wave actually reflected, there's no change in medium. The medium will still actually remains the same. So we talk about reflection, actually nothing changed except maybe the direction of the travel. Okay, while the wave is going forward, after reflected, the wave is actually going backwards. So for reflection, the only thing that changed is actually the direction of motion. Okay, direction change. The rest actually remains the same. Okay. For refraction, usually occur where across medium. So when you go from medium A to medium B, okay, or it could be from a shallow region to a deeper region. There's a change in the environment given. So for refraction, the direction or direction will not change. Actually, direction will remain the same. Okay, but the motion, the motion actually will change. Okay, because we are going through different depth. Okay, so actually when we go from shallow to deep region for water waves, you'll find that actually the wavelength of the wave and the speed of the wave actually changes. Okay, and what actually remain unchanged in this area is actually the frequency of the object, frequency of the wave. The frequency of the wave actually remains unchanged. Okay, it can actually remain unchanged. So if you look at the direction, if you look at the properties of the water wave when it go through refraction from shallow region to deep region, you'll find that actually the frequency of the wave actually remains unchanged. The lambda and the speed of the wave actually changes. So automatically the answer only for B. Okay, so if you want to look at how the water wave actually changes, you just have to take note when you, water wave go from deep to shallow. Let's say from deep region to shallow region. Okay, when you go from shallow region, you actually find that the speed of the wave actually decreases. The speed actually decreases. The wavelength actually decreases. Okay, so these are some of the characteristics that we might want to take note of it. And likewise, if I go from shallow to deep, the speed will actually increase, the wavelength will actually increase. Okay, so but one thing, whether regardless of the depth, whether from deep to shallow or shallow to deep, okay, the frequency of the wave actually remains unchanged. Okay, so these are the things that you might want to take note of it. Okay, for question 10, okay, we look at the displacement time graph, okay, of a wave. The displacement time graph, simple characteristics. Okay, you will know that for a cycle, for one cycle of the wave is from, let's say, from one cycle of a sine curve, you look something like this. This will be the one cycle. One cycle for displacement time, because the x-axis, the horizontal axis is time. For one cycle here, it's actually represented by one cycle. Okay, but it's time for one cycle. Time for one cycle refer to the period of the wave. Okay, capital T. Yeah. And here we have for displacement time graph, the equilibrium position to the crest. Okay, this is what we call the amplitude, okay, of the wave. These are some characteristics of the wave that you might want to take note. Given that the wavelength is 0.1 meter, okay, given a wavelength 1.1 meter, how long does it take to travel 100 meter? Okay, time taken for the 100 meter. So maybe what we want to do is we could actually get the speed of the wave first, get the speed of the wave, V equal to F lambda. Okay, so the frequency of the wave, okay, if you look at the math, okay, period is actually frequency is actually 1 over T. Okay, so they are inverse relationship. So if I have the period, which is based on the question is 2 seconds, which is 1 over 2, which is 0.50 Hertz. Okay, and I know the wavelength is actually 0.10 meter. Okay, so if I substitute these two numbers into the formula, I should be able to get the speed of the wave, which is, let's take a look, 0.5 multiplied by 0.1. Okay, let's use calculator. Okay, 0.1 times 0.5, I will get 0.05 meter per second. Okay, so if the speed of the wave is 0.05 5 meter per second. Okay, so it's constant speed. Okay, so speed will be distance divided by time. Okay, so I would say I need time to travel. So the time to travel, how long? 100 meter. Okay, 100 meter, given the speed is 0.05, how long do I need? Okay, I will need 2000 seconds. Okay, answer solved. Okay, so this will be the question that we have. Okay, so you take note, if you look at this question, right, I would say it's a simple question, but it doesn't mean that you have like use one formula and the answer will appear. So if you look at the question, right, although it's a simple question, the mathematical involved, the thinking that we involve is a two-step thinking, whereby the student actually need to interpret the data from the graph to elicit the frequency. After that, they have to proceed on to using the standard wave formula V equal F lambda. Okay. Then to calculate the speed of the wave, and from there, I proceed on to calculating the time of the wave needed. Okay, so I would say this is 2A and this is 2B. So they are like together. Okay, so you look at the calculation involved or the thinking involved for MCQ question. Okay, it doesn't mean MCQ is actually straightforward. One step answer, you get all the answer that you need. No, one step working, you get all the answer. No, okay, because sometimes the MCQ actually it can be quite tedious or it can be quite in depth. Okay, so students, you have to prepare for like in-depth analysis. You have to do that very fast. Okay, because for MCQ, you have like for this paper, you have 1 hour. Okay, you're supposed to finish 20 questions physics, 20 questions based on chemistry. So a total of 1 hour for 40 questions. Okay, so it'll be quite time demanding. Which of the following is transverse wave? Okay, I would say it's quite straightforward. Okay, for transverse wave, you must remember there's a transverse wave, there's a longitudinal wave. Okay, longitudinal wave, I would say the most straightforward, the longitudinal wave. Okay, in our syllabus, it's only for sound. Okay, sound is the only longitudinal wave that we have. So whether you have infrasound, ultrasound, sound, audible sound, okay, they are all classified as longitudinal wave. And the rest of the wave that's not sound actually are transverse wave. So the easiest one is to actually get rid of whichever sound, whichever option that has sound. For example, ultrasound. The moment I ultrasound, this definitely is a longitudinal wave. It's definitely not a transverse wave. Sound wave is definitely a longitudinal wave. So likewise, okay, infrasound, same thing. Infrasound, anything to do with sound, ultrasound, infrasound, audible sound, they're all longitudinal wave. So if I want the transverse wave, the only option that doesn't have any sound included is actually option B. Okay, so please be careful about the option, especially when we look at infrasound and ultrasound. Some students may get mixed up with infrared radiation and ultraviolet radiations. Okay, so take note of the small little tricks that we always like to use. Okay, first for your EM spectrum, same thing. Remember your EM spectrum. So let's say example for under ultraviolet, the region where it's under ultraviolet, let's say example D, this area will be what we call the gamma rays. Okay, the symbol for gamma ray. Okay, so you must know how the wave is actually being arranged. Okay, likewise, if I know this side is red, the other end, extreme end, will be infrared. And then at the most extreme end here, if I'm not wrong, it should be radio wave. So for EM spectrum, okay, students, you have to actually remember how the wave is being arranged, whether it's in terms of frequency or arranged in wavelength. So you must know what are the waves that are being structured. And after that, you need to know, okay, what are the users? What are the users, or what are the pros and cons of the waves itself? Okay, for example, gamma rays used for cancer treatment, X-rays for looking at beneath the skin layer, or even to identify cracks in the wall. Okay, so you need to know what are the users, what are the arrangements for under the EM spectrum topic. Okay, so you have to actually do your own homework for this. Okay, for question 13, right, if you look at it, it's a classic example of pitch and loudness. Okay, for loudness, we have to take note, if you look at loudness, we are actually looking at the amplitude of the wave. Okay, and likewise, the louder is the sound, the higher is the amplitude. The other aspect of the graph that we're looking at is pitch, high pitch or low pitch. So if we're looking at pitches, we're actually looking at the frequency of the graph. Okay, the frequency of the graph. Okay, and similarly, the relationship high pitch means high frequency. Some of us, we would like to look at it in terms of, let's say, the period of the graph. Okay, and like we all know, the period and the frequency is an inverse relationship. So the higher the frequency, the shorter is the period of the wave. So indirectly, we are also saying that the pitches, okay, when the frequency increase, we are also looking at the period, okay, having a smaller value. Okay, but the common, I would say the relationship between pitch is actually tagged to frequency. Yeah, and likewise for loudness, okay, loudness actually tagged with amplitude of the graph. So let's say for example, this question, if you look at the axis, again, Tom wave, Tom, the amplitude is actually 1 square. For Harry, the amplitude of the wave is actually 2 square. So straight away, you will know that actually in terms of amplitude, okay, amplitude, okay, Harry amplitude is definitely much bigger than Tom's amplitude. So which means Harry wave will actually be louder as compared to Tom wave. So Harry will be louder, okay, as compared to Tom, or what we call Tom is actually softer than Larry. So straight away, I can actually eliminate option A and option D already. Okay. Then after that, we look at the other aspect of the wave itself, with the frequency of the wave. The frequency of the wave for one cycle for Tom is actually 2 square. It's spanned across 2 square. I would say the frequency at the period of the wave is here. The period of Tom is here. Okay, so I'll say T for Tom, period of Tom. And likewise for Harry, the frequency for Harry for one wave is actually span across 4 cycles. So definitely the period is here. This is okay. So you look at it, you will know that the period for Harry is actually longer as compared to the period for Tom, which means that the frequency of Harry would definitely be smaller, okay, than Tom. Okay, if frequency of Tom is higher, it will definitely mean that Tom pitch, the pitch of the whistle will actually be much higher than Harry. So you effectively lead us to this option B, whereby talk about Tom having a higher pitch as compared to Harry. Okay, so if you look at the way I solve this particular question, it's a standard approach whereby we look at the sound graph. Okay, we look at amplitude, we look at the frequency. Why we want to look at these two important things? Because amplitude is actually tagged to your loudness, frequency is tagged to your pitches. Okay, so to know the pitch, I will look at the frequency, or what we call the period of the wave. Or if I want to look at the loudness, I actually look at the amplitude of the wave itself. Okay, so this is what we call the standard approach of looking at the loudness and pitches. Okay. Chapter 14, electrostatic. Okay, electrostatic, light charge, keyword, light charge repel, unlight charge attract. Okay, so these are the few things that we always look at it. Light charge and unlight charge. Okay, one repel, the other attract. Okay, so these are the two main phenomena if you look at electrostatic. And the other one that we look at is actually what we known as a charge distribution. Okay, for example, we will know that if it's positive charge, the charge will actually, they will not actually they will not be actually like spread out in a certain manner. So if I have a charge distribution of a positive and negative, you will find that the charge distribution actually will be of a certain pattern. And that particular distribution pattern is actually how we decide whether the charges actually being allocated in the correct position or correct location. For example, right? First thing we look at is the distribution. For example, right, if it's positive charge on the right, negative charge on the left, okay, because we know that unlike charge attracts, wrong statement. Unlike charge attract. So you'll find that if you talk about the charge distribution, because of attraction, the positive charges and negative charges should actually be close to each other. Okay, for example, if I have two sphere, okay, if positive and negative charges, instead of moving away, okay, the charges should actually be near to each other, because why? Unlike charge attract. So the two charges will be actually attracted together, trying to touch each other. So if you look at the charge distribution, it actually should be more towards the center. Okay, so that's why option C is out, because the charge distribution is wrong, even though the direction of the forces is correct. Okay, so option C is out. A will be out. A definitely, if it's light charge, okay, light charge, it definitely have to repel. So you look at this arrangement of the charge distribution, these charge distribution are actually going towards each other. So they are like attracting, but because they are light charge, they should be repelling from each other. So the arrangements, the charge arrangement, charge distribution for the charges on this object should actually be placed further away, So the charges should be further away from each other. Why? Because the positive charge actually they repel from each other. They don't like each other one. So they will actually try to stay as far away from each other. So they should be on the extreme ends of the sphere itself, one on the left or one on the right. Okay. Correct distribution should be something like B. Okay, whereby the charge distribution is actually far away from each other. Okay, because they are light charge and the force actually should be talking about repulsions. Okay, for D will be the reverse of C. Okay, so the charge distribution is the correct placement. The plus and minus, they are attracted towards each other. So unlike charge, they should be attract. The forces should actually be opposite direction, should be here. Okay, in this side, they should be attracting each other. Okay, so for charge distribution, okay, the standard arrangement we are looking at is positive charges, how the field, the charge distribution of positive charges, how the charge distribution on negative charges on the objects. After that, we will be looking at the field pattern, the electric field pattern, okay, of all the charges. So these are the common thing. If you look at a revision, you should be touching on them. So in terms of when you revise electrostatic, you should be looking at the arrangement of positive charges, why the positive charges are arranged in this way, what are the keywords dealing with it, and eventually the last segment will be on the electric field, pattern of the electric field patterns of the arrangements. Okay, and electric field pattern, they are like a standard fixed arrangement, between positive charges, between opposite charges, and even a parallel plate. Okay, so these are the few patterns that we will want to actually take note of it. Okay, and all this, if I'm not wrong, it could be easily found in the textbook or in the notes that you have actually. Okay, rubbing, okay, gaining of positive charge and negative charge. Okay, so we'll take a look. Okay, so if you look at charging by friction and rubbing, okay, charging by friction. Okay, usually charging by friction, one of the characteristics that why I would want to use charging by friction, okay, but we use rubbing is because the two objects that I have, okay, are actually non-metal. So this is a method that is actually commonly used for non-metal object. For example, glass rod, perspex rod between cloth, cotton cloth, balloons with rubber, rubbing with cotton cloth or maybe silk cloth. These two are like non-metal. So for rubbing, charging by friction, this particular technique is actually more pertaining, more suitable for, more appropriate for for non-metal objects. So primarily for non-metal objects, if you look at the two options, the only option they have non-metal objects is actually option D, polystyrene rod and your wooden duster. So automatically the first instinct I know, since the technique is for non-metal objects, I will actually choose D straight away. Yeah, I will not even be touching on C, because C I have one which is non-metal rod versus a steel magnet. Steel magnet is still a conductor, so I will actually try to avoid that. Okay, so for technique wise, if you look at charging by friction, we always usually use it for non-metal objects. Okay, so that's how I eliminate my answer and choose D straight away. 16 and 17 is more on a circuit question. Okay, component X. Okay, here, what is component X? You have to take note with the arrow, rectangular box with the arrow. This is what we call a rheostat. Okay, or sometimes what we call a variable resistor. Okay, variable resistor, the main purpose, of course, like what the name mentioned, variable resistor. I want to vary the resistance. Okay, the main component for variable resistance. Okay, one thing is actually to change the resistance of the resistance of the circuit. And indirectly, what I'm trying to do is actually I'm trying to actually adjust or regulate the current flowing in the circuit. Okay, I want to control the current flowing in the circuit. I don't want the current to be too big, or maybe I want the current to be a little higher. So what do is I will actually change the rheostat value to regulate the current in the circuit. Okay, so that's why I will know straight away I will choose option A. Okay, change the resistance indirectly. After that, I will actually change the current in the circuit here. For C, for 17, okay, the ammeter here, same thing here, we're looking at is the property of parallel resistance. Parallel circuit, take note, parallel circuit, current come out from the battery. The moment I hit a junction, the current will actually split up into different branches. Okay, so this is what we call I total. Okay, it's being split into I1, I2. Okay, if you look at it in terms of math, it will be something like this. And this property is what we have for your parallel circuit, whereby current actually splits up at different nodes or at different junction. Okay, and of course, the other aspect that we look at is actually current is actually inverse related with your resistance, meaning the higher the current, okay, it will imply that the resistance in the circuit is actually lower. Okay, resistance. The word resistance means I resist current. Okay, the bigger the resistance, the smaller the current will flow. So if I want the lowest reading, the lowest reading, definitely if you look at the mathematics, I will not choose IT. Okay, IT will in fact be the biggest because sum of I1, I2 will definitely be equal to IT. So IT will definitely be much larger than I1, I2. So if automatically I will know A is out, so it's only left with I1 and I2. Okay, if A is out, D is out. So because they are actually measuring the same current, which is IT. So I1, I2, I2 is actually measured by, I1 is measured by ammeter C, I2 is measured by ammeter B. So which will be higher? So we look at the second property that I mentioned, the relationship between current and resistance. Okay, the higher the resistance, the lower the current. Okay, so if I want the lower current or lowest reading ammeter, I will definitely choose the one with the higher resistance. Okay, which is ammeter B. So ammeter B will definitely give me a smaller or the smallest current reading because it has the highest resistance in that particular branch. Okay, so these are some of the basic facts about parallel and series properties that the students that you guys will have to know it by heart. Okay, to understand the beauty about the parallel circuits, what are the properties that behind the parallel arrangements. Now for 18 is a bit of calculations. Okay, here what we look at is the distribution. Okay, the easiest, I would say, there are a few ways to do it. Okay, the most common way is actually to look at the current in the whole circuit here. Okay, so this is a current flowing through the circuit. Okay, and the total current here, we are looking at the most straightforward is use Ohm's law. Okay, so if I want to find the total current flow in the circuit, I will want to know the total voltage potential difference across the circuit and the total resistance in the whole circuit. Total potential difference in the whole circuit is what we call the EMF of the circuit, which is 24 volts. Okay, so there's 24 volts, current I1, total resistance 60 plus 20, 60 plus 80, 60 plus 20, which is 80, which is what we call resistor in series. So this 80 ohms. So if you use a calculator, you'll find that the current in the circuit would be a nice number. Okay, 0.3 amp. Why would I want to find IT? Okay, because why? Because based on the question, I want to find the potential difference across 20 ohms. So if I want to find the potential difference across 20 ohms, what I actually need is I will need the current flowing across 20 ohms and I will need the resistance of 20 ohms. Okay, so if I know the resistance of 20 ohm, which is 20 ohm, the current that's flowing through the 20 ohm, the current that's flowing through the 20 ohm would be actually the current what we call IT. Why? Because the two resistors are in series, so current flowing around the circuit in the series circuit will actually be the same, being constant. So current flowing across the circuit will actually be the current flowing across 60 ohms and the 20 ohm resistor. So likewise, if I put the value in 0.3, substitute inside. Okay. Press your calculator and you get the answer to be 6 volts straight away. Okay, so answer would be B. This method of doing, I would say, is the basic using of the formulas. There are other ways of getting the answer 6 volts. Okay, some can be fast. Okay, some can be using the potential divider rules. Okay, the potential divider rule whereby you can actually get the answer straight away. Okay, so if you need to know like other method of solving, you can look at my other videos in circuit. Okay, but as for now, I will leave the basic formulas, the basic solving technique of using Ohm's law, finding currents, okay, finding the voltage, the current across the circuit, and finding a potential difference across the resistor. These are what we call I would say, the basic, the underlying principle of or the formulas that we use to solve circuit, which will always can be used in any arrangements. Okay. Question 19. Question 19 is a circuit question again. Okay, if here what we testing, or what the marker is trying to test the students is actually to interpret from an actual diagram, the real life application, and actually to interpret it to a circuit arrangement. Okay, same thing. The important thing is you look at the question, you see this plus sign here, the positive terminal of the batteries. So they are actually, one side is plus, automatically the other side of the cell will be negative. So if you look at the two cells, they are actually connected in the correct arrangement, in series arrangements. Okay, so once I know the cell is in series arrangements, you look at the wire. If I have the current coming out from the light bulb from the positive terminal, you'll find that I will come out from the positive terminal, follow through the wire to the switch. Okay, oh, sorry. I shouldn't be from the wire. Okay, coming out from the battery. We're coming out from the battery, going up to the light bulb. After that, you'll go to the wire, okay, before and going back to the cell itself. So you'll find that the current actually flow in a single direction and there's no junction across along the way. So the current actually remains the same. So these particular specifications or this particular pattern will imply that the arrangements for all the components are actually in series arrangements. Okay, because the current actually remains the same, there's no splitting up. So automatically straight away, I will know option D is out, option C is out already. Okay, because option D and C involves parallel arrangements. Okay, so you only left with option A and B. And because I know the cell are actually arranged in the plus minus in the series arrangement, plus to minus, plus minus, all these things. So I will know the option would be actually, my answer will be option A. Okay, which fits the characteristic whereby it's a series arrangements. Okay, and the cells are actually placed in the correct positions. Okay, so that's why option A is the answer that I would choose for my for this question, not B. B, you take a look, the terminal are actually opposite in direction. The plus and plus, the minus are actually the negative and negative terminal. The positive terminal and the positive terminal are actually placed together. Okay, so take note of the arrangement. For question 20 is a fuse question, same thing. Correct arrangement of fuse straight away. Okay, the moment say where should fuse be connected, this one I would say most all the students you have to take note is like the location of fuse and switches. They have to be placed at the correct position for it to work effectively as a safety precautions. Fuse and switch has to always has to be placed at the live cable. Okay, the live wire, okay, for them to work effectively, to work correctly, to be exact. Okay, so automatically I will know option A and option C is out because they say it is in the neutral cable. So only left with option B and D, which is the correct answer. Same thing, fuse, yes, I do know that the most common arrangement that we have, okay, for fuse, if you see in daily, it's like 13M. You see 13M fuse being used very commonly. Okay, it is because of the arrangement or the calculation of the current that we have. It could be like maybe 10M or maybe 11M. So the next best reading for fuse is actually 13M. Okay, so when we talk about usage of the correct fuse rating, which type of fuse rating we use is not like 13M is being the common, or I will just use 13M regardless of my calculation. No. Okay, it's not this way, right? For fuse calculation, for fuse rating, the primary rules that we are looking at is we always choose the next best rating. Okay, the next best, the most appropriate one. Okay, not the most commonly available. Okay, so the next best arrangement, for example, if my current rating is 10M, the next nearest value that I have for fuse rating is actually 13M fuse. So I will use a 13M fuse. If my current is 1.2M, I will not want to use a 13M because it would be too high really to be effectively used as a safety precaution. So if my working current is 1.2M, the next best rating, the next possible fuse rating that I have in the syllabus is actually a 2M fuse. So instead of a 13M fuse, in this case, I will actually use 2M fuse because that it will be the next best, most appropriate rating for my particular current in the circuit. So if my fuse rating is actually 3.5M, okay, the next best appropriate readings I will have is actually 6M fuse. That will be the best. Fuse rating that I have. Okay, not 13M fuse. Okay, not 13M. So if you look at option B and D, the next best rating for a 3.5 working current, it will be 6M. That will be the most appropriate readings. But of course, is this the correct reading? I will not know. It depends on what the market is available. So if the market has, let's say, a fuse rating on, let's say, 5M, I would definitely choose a 5M fuse rather than a 6M fuse. Okay, so it depends on the particular appliances that you're looking at, what are the current rating, what are the working current you're looking at. Okay, but for this case, between 6M and 13M, my best option I will choose is actually 6M. So that's why my option will be D. So in terms of fuse rating, students, you have to take note while you do your revision, you have to take note of what are the commonly common rating for a fuse, so that in exam, like in this case, you will actually choose the correct fuse rating. Okay, so with that, okay, we will move on to two question. Okay, question 1 here refer or will need you to use the vector additions, okay, parallelogram or tip to tail, whichever is convenient. But it's an interesting question because this question actually requires the students to actually work backwards. Okay, the normal pattern that we have is, I would say, the normal questions that we have is usually the question will give you, will ask for like, will give you like the magnitude of T, okay, and they'll give you the magnitude of the forces, or the force. Then after that, they will expect you to find the resultant force of both of them. Then after that, maybe the extension for this is maybe the question will require you to infer that the resultant force is actually being balanced. It's actually will be balanced with another force, maybe a third force. Okay, in this case, it might be the weight, okay, of the object. Okay, a third force. Okay, usually this is the common approach or the common pattern or style of questioning that we deal with when we look at vector addition. But what's interesting about this question is that it actually go the reverse. Okay, what happened is that the question actually give you first the resultant force. The y is going to be balance of the third force, okay, the weight. Then what the question requires the students to do is actually the reverse, as in once I give you the forces, the question requires the students actually to infer or to deduce the possible magnitude for T and the possible magnitude for your F, okay, the force from the fan. So from the resultant force, they expect you to deduce the possible two magnitudes and the direction of the two component. Okay, so this is what interesting about this particular question. It requires the student to actually reverse their thinking, okay, and actually to work out the answer. Okay, so now let's look at how we're going to solve it. Okay, there are a few ways to do it. Okay, some we have this third force three force closed triangle method. That's one way of doing it. Okay, if you're familiar with it, by all means go ahead and use the closed triangle method. If not, okay, we'll stick to the basic of see how we use a parallelogram method. Some of you are, if you're familiar with tip to tail, by all means go ahead and do. Okay, in this question, I will use the parallelogram methods to see how we can deduce the answer. Now, for the question before doing, okay, just take a look. Okay, since we are given the weight of the ball itself, so you just take note of some of the simple conversion. The ball is given is a 410 gram. 410 gram is literally 0.41 kg, and 0.41 kg is actually equivalent to 4.1 Newton. So if you look at in terms of vector addition, the forces, okay, the weight that's given, okay, the weight of the ball is actually 4.1 Newton. That's what we are going to actually derive the thing. Now we also know one thing is because the question says 4.1 Newton is the weight. Okay, so if it's the weight, there is a few things that I will know. I will know that the weight is a vertical force. Okay, and it's actually from the ball itself. Okay, or it acts on the ball itself. Okay. So these are the two information that I know. So inherently, that before I start solving the question, I actually know the outcome already. I know that the ball has a weight of 4.1 Newton acting on it. And this force weight is going to balance, it's going to be balanced, okay, it's going to be carried by the two resultant force of of T followed by F. Okay, so the resultant force of T and F, the magnitude will actually be the same as 4.1, will be 4.1 the resultant, and the only difference is that the resultant force of T and F, okay, I will know that the answer will be 4.1 Newton, and it will always be in opposite directions as compared to the third force, which is the weight. Okay, so effectively I actually know that the resultant force, okay, of the object, okay, is actually 4.1 Newton. RF, the magnitude of RF, okay, the magnitude of RF will be 4.1 Newton. Okay, and I also know the direction, it will be totally opposite, 180 degree, okay, with respect to the weight of the ball. So I will know that it will be acting vertically upwards. Okay, so this is the clue that I have from the question. So that's what the clue is trying to tell me. Well, the question is trying to tell me when they give me the clue to say that the weight, okay, is going to be balanced by the two forces T and F. Okay, so the resultant force of T and F add up, the magnitude will be 4.1, direction will be vertically upwards. Okay, so you can use a appropriate scale depending on the size of the paper. So in general, there isn't a nice number to use, but I would just say try to maximize the paper or your drawing so that it can actually cover the entire space, the white space of the question paper. So it could be possible that it could be I could use a 0.5 Newton. Okay, so 0.5 Newton, if you look at it, it will be effectively for 8.2 cm. In this case, it will be like 8.2 cm. Okay, so what I do now is, given a space, so I will actually draw the 4.1 Newton RF. Okay, you'll be pointing, let's say you're pointing vertically, okay, upwards. Okay, so this will be pointing vertically upwards. This will be RF. Okay, act on the ball itself. And this magnitude here will be 4.1 Newton. Okay. Bracket wise, it will be the dimension 8.2 cm. Okay, so the black one, remember, you have to write. Okay, so now what we know is this is the first clue that's given to us. The resultant force is 8.1. The other force that I also know that is that on this particular object, the ball, two other forces act on it. And it's because of these two forces, I have a resultant force. And the two forces I have is actually F is a horizontal force, totally vertical. So I will know that F actually looks something like this. F is actually 90 degrees with respect to your RF. Okay, because F, okay, it is horizontal force, so it definitely has to be 90 degrees. But I will not know how long it is. Okay, but I do know that in terms of direction, F will be in the horizontal direction. Okay, so this is F. Okay. Oopsie, sorry. So now what I have is the horizontal force. Okay, so this is F. Okay, but how long F is, I don't know yet. And the other information I have is I also know that, okay, T is 30 degrees. Okay, T is given in the question, T is 30 degrees. Okay, given in the question, T is 30 degrees. Okay, with respect to the vertical axis. So what I will actually know that, okay, T, let's say if you use a protractor, okay, you'll know that the 30 degree here is actually 30 degree with respect to the vertical. So T is 30 degree with respect to the vertical. So I will actually, if I use a protractor, let's say if you use a protractor, 30 degrees is roughly this angle. So you use a protractor, okay. So it will be 30 degree. This is where T is going to be. Okay. So let's give a big one. Okay. So let's say if I measure 30 degree, it will look something like this. Okay. T will be in terms of in this direction. This is where T is. Okay. But now, okay. So this is T. But although I do not know the magnitude of T and F, but I do know that the resultant force, okay, the resultant force of T and F would be equivalent to your resultant force. So if I'm going to use a parallelogram method, okay, so eventually whatever magnitude I have for this horizontal distance, take a look. Okay, this horizontal distance, what I do is in parallelogram method, if I assume this is the resultant force, I will actually copy and paste. Okay, I will actually drag the parallel line to where T is. Okay, and in fact, I also know that how long the blue line is, how long F has to be. Okay, it must actually occupy the space between. It must occupy the space between RF and T. So the intersection point here will tell me this is the length of T that I need. Okay, so with the length, I will also know that the magnitude for F itself. Okay, because I know that T and F, okay, they must form a closed parallelogram, a closed rectangular, closed rhombus shape that we're looking at, a parallelogram shape. Okay, so I know that the magnitude of T is not infinite one. The magnitude of F is also not infinite because I know that T and F, they have to make up a closed triangle shape. So what we do now, let's say for this case, let's say Okay, so if I have F at this junction, I also have T. Let me copy T. Yes, okay. So let's say I copy T. T, I also know it will form, I will shift it, it will form a closed shape, okay, with respect to the, okay. So T will also, I also know T, okay, it will have to form the length of T, it will have to form a closed rectangular shape, okay, a parallelogram shape for the RF itself to give you RF. So I will know that T is actually from here all the way to here. Okay, so the intersection point of these four lines will give me the correct magnitude for F and T. Okay, so from here I will know the exact number, exact magnitude, exact length of the T and F. Okay, and from there I will actually, what I'm doing is I will actually erase the line. Okay, erase my line. Let's say I do a green color one, add more colors. Okay, so what I do is I will take eraser, I will actually erase my line. Okay, I erase my extra line here. Okay, I'll erase my extra line. Okay, and this is the correct length for T and F. Okay, so let's say, so this will be the correct length for T and F. So this will be the correct dimension for T and F. So what I lack now is actually direction. So direction of F given is vertically, sorry, horizontally to the left. T is in the upward direction, 30 degree. Okay, and with this, I will know that this is the correct orientation or the correct magnitude for T and F. Okay, because I know that these two lines will actually add up to become the resultant force. So once I have this drawing, what I do now is I actually literally take a ruler and I actually measure the dimension for the length of the cable, the length of the drawing, length of T here. I will measure the the length of T. Okay. Then after that, I will get the answer, and the length of it will be actually the answer. Okay, and if you do it accurately enough, you can do a bigger drawing. Maybe 1 to 0.5 is the minimum scale that I need. You can use 1 is to 0.25 or 1 is to 0.4 Newton. Is okay one. Okay, as long as it fit the space. Okay, so if you do it correctly, the magnitude for T will be in the range of 4.5 Newton. Maximum I'll go is 4.9 Newton. Okay, the maximum of F will be 2.1 Newton to 2.5 Newton. So this is the range for F. Okay, and same thing, like I want to repeat again, you might want to measure, okay, the length of the F and T to get the magnitude for them, for these two forces. Okay, so what I have done now is I actually have worked backwards. Okay, from the resultant force, actually I work backwards to form the parallelogram shapes. After that, from the parallelogram shapes, what I did is I actually measure the length so that I can get the individual magnitude of the component forces. Okay, so this is what we mean by using parallelogram to find the resultant force. Okay, but the only difference is normally I will actually be given T and F, then I will be required to find resultant force. So what's interesting about this question is it actually do the reverse. I'll give you I was given the resultant force, and I'm supposed to find the component T and F. Okay, which is what makes this question interesting. Okay, so if you are still not sure about how I'm going to look at it, you may want to rewind the video to take a look at the steps that I did. Okay, I may not have give you a clear explanation. Okay, because it's more like a technique. Okay, so to do this, you really literally need to know the technique for your parallelogram method and or tip to tail. Okay, so if you have forgotten, okay, your parallelogram tip video, how to use a parallelogram or tip to tail method, okay, you can refer to my chapter 3. Okay, chapter 3 video, okay, on parallelogram method and vector additions. There is actually 2 videos on it. Now for question 2, okay, question 2 is a classic velocity time graph question. Okay, so now, okay, when I initially fall from the stone, is initially fall from rest. Okay, fall from rest, remember, fall from rest, the clue behind this is that the initial speed is actually 0 meter per second. And usually fall from rest, okay, you also imply that it's under the falling under the the influence of gravity, gravitational field strength. So which means the acceleration of the object will be actually 10 meter per second square. That's what that statement from rest, falling from top, is actually what the clues that the marker is trying to tell us. Okay, these are the two clues that is trying to tell us. The initial speed is 0, the acceleration is 10 meter per second square. Okay, and then after that, the question move on to say it takes 3.6 seconds to reach the ground. Okay, so definition of define the acceleration of falling stones. So because I know it is falling, okay, so I know it's under free fall. So like I mentioned, it will be under the acceleration will be 10 meter per second square. The initial speed, okay, the initial speed formula, remember to calculate free fall, the common formula that we use is velocity is change in the acceleration is the change of velocity per unit time. So it'll be final minus initial divided by time. Okay, so what is hidden is that the students need to know that the acceleration is 10 meter per second square. Then if I have a time and I also know the initial speed is 0, you get the answer 3.36 meter per second straight away. So I would say it's quite a simple question. Okay, but of course, the important trick here is that the students need to know what is the clue that the question, what are the clues that the question is trying to give you. Okay, then after that, draw the speed time graph for the objects. Because I know it's 10 meter per second square, and I know that in terms of velocity time graph, this will actually be what we call the gradient of the graph. So I will actually have a constant gradient, which means it's upward sloping straight line. So this will be the line that I have. And the height of the cliff. Height of the cliff, you look at kinematics, okay, two things that I need from the graph of the gradient. The graph is I will need the gradient of the velocity time graph. Then the other one that I usually like is I will need the area under the graph. Okay. The area under the VT graph will actually give me the distance traveled by the cliff itself. Okay, or by the boy, okay, which is actually the distance traveled. So between the area under the graph for 3.6 meter, okay, it's actually literally what we call here the area under the graph. Okay, this is the area that I need. So the area that I need, the distance that I need here is actually the triangle. Okay, the area of the triangle is half base times height. Okay, that's where the half appear. Okay, not because of like some magic number or this. No, the half actually appear because the shape of the graph is actually below the 3.6, below the graph within the 3.6 seconds range is actually a triangle. That's why I know the area on the graph will actually be the distance traveled, and I also know the formula is half base times height. Okay, so it's a classic question. So I would say question 2 is like a safety net question. It's like supposedly most students should actually get it in the pocket one. Likewise for question 3, okay, micrometer screw gauge, we look at 0 error. Okay, 0 error for based on this question. Okay, same thing. I will not dwell too much on this question because this question is a very straightforward classic recall question whereby the students, they are supposed to know what are the 0 errors, how to read the 0 errors, and actually do the correction for the readings. But of course, the common trick that we like to use on students is actually the use of the word diameter. Sometimes the question may ask for diameter, okay, which is actually the correct answer, which is the exact answer. You don't need to do any manipulation. Sometimes the question will actually be a bit tricky to say that they ask for the radius of the object. So if I'm looking for the radius, radius, as we all know, is actually half of diameter. So whatever number that I have from the micrometer screw gauge, I will need to divide by 2 to get the radius. So these are the small tricks that we actually like to play with the students to make sure that students actually know what they are doing. Okay, so radius, diameter, some area, all these things. Okay, so take note of it. Question 4. Question 4 is a simple, I would say it's a simple Newton's law question whereby 24 kg couch, okay, so far is given a horizontal force. So the force exerted is actually 60 Newton. The mass of the object is actually 24 kg. Okay. And the question is given that there is a friction. It's given already. The question is mentioned there's a friction. So there is a friction 30 Newton. And one of the common trick, or one of the common questions they always ask is they will ask you draw the forces. So if you look at friction, remember friction has to be drawn at the surfaces. Okay, the contact surfaces. So I would say the contact surfaces will be at the sofa, the leg of the sofa. So I'll just summarize all the friction by all the legs. It could be 4-leg sofa. So all the friction will be at the legs. So it'll be governed by this force. Friction is equal to 20 Newton. Okay, remember where I draw the friction, it should be drawing at the surfaces, the contact surfaces. Okay, so same thing. Once you have it, you will apply there are 2 forces acting on the sofa. So the common formula will be F net equal ma. Two forces that I'm looking at is 60 Newton and 20 Newton. So here I go. Okay, the mass given is 24 kg. Make sure it's in SI unit. After that, we'll be able to find the acceleration of the sofa given using the formula. So nothing, I'll not say it's difficult. Okay, so just take note of it. Then the second one is they tell you that the force remains the same. But now what they did is they have a wet floor. Wet floor, remember, wet floor means slippery. And wet floor means the friction actually has been reduced. Okay, so what happened is when we say talk about friction is reduced, we are looking at the friction is reduced, the applied force remain the same. So I would definitely know that the resultant force, which is the keywords, okay, definitely has increased. And resultant force increase, it also means that the acceleration of the object will also increase. Okay, so that's why the motion of the object actually get faster and faster. Okay, now what happened to the work done by the 16 Newton? So what happened? Okay, so when we talk about friction here, I push the object, it gets faster and faster. So when the object gets faster and faster, because there is an acceleration here. Okay, because I mentioned there's an acceleration here, so the object is actually, the sofa is moving faster and faster. Okay, so what we call the velocity actually increases. And when I say velocity increase, it automatically means the kinetic energy actually possessed by the sofa actually has increased. And remember, the question talk about friction. Okay, the question talk about friction. So there will be definitely friction along the surface, whether it's wet or dry. Based on the question, even if it's a slippery surface, it still has friction. It just reduce amount only. So there is still friction, so there will be work done against friction, or sometimes what we call heat loss between the contact surface. Okay. Okay, contact surface of what? Of the sofa and the floor. Okay, so I will need, so if you use heat loss, I will need to know heat loss, and I definitely need to know the location. Okay, so remember when we talk about heat loss, don't just write heat loss to environment, heat loss to environment. Okay, the students have to be very specific. You talk about heat loss, you have to tell me where does the heat loss come from. Okay, and where does heat loss go to? Okay, it's quite obvious going to the environment, but what I need students to know is to actually deduce where is the friction, where is the heat loss occurring at specific location. Okay, so that's what we mean by the keywords when we look using heat loss. Now, for question 5 is an interesting question when we look at the ball being struck off from the golfer. Okay, the motion that the golf ball actually move. Okay, this curve here, this parabolic curve is what we call projectile motion. Okay, but what we need to know is in our syllabus, okay, when we look at the object being traveling in this curved path, this parabolic path, the path that we're looking at, this is what we call the highest location. Okay, the highest location here, you must remember, there are a few clues behind this particular location. For all highest location, there's a few characteristics, which means, firstly, the vertical distance is always the highest. That's why it's called the highest position, right? The vertical distance is the max. Okay, but you'll be surprised that sometimes, okay, at the highest location, okay, the vertical component, the vertical distance, the vertical component, okay, the vertical velocity actually is the smallest. It's actually 0 meter per second. Okay, so there will be a minimum speed happening at the top of the thing, okay, before it starts off. Okay, so now based on the question is the ball is 45 gram. Take note, 45 gram. 45 gram not SI unit, so I need to convert it to kg, which is 0.045 kg. Okay, so take note of the booby trap. Remember to convert, because if you look at energy, all the factors, all the variables that I substitute into the equations has to be in SI unit. He transferred 38 joules, okay, as the club hit the ball. Okay, so which means at the beginning, he will be actually traveling at a speed, and that speed is controlled by the amount of energy that the ball has, and the amount of energy the ball has at the beginning is 38 joules. It's totally converted to the velocity. If not, it will not fly actually. So at the beginning here, at the beginning stage, the energy available here is actually kinetic energy. Only kinetic energy, because it has not lifted off from the ground. So it only have kinetic energy. So all the energy will be converted to kinetic energy, which is half mv squared. I know the mass is 0.045 kg. Okay, I will definitely be able to calculate the speed of the ball itself using the formula half mv squared. Okay, so I would say it's quite easily done. As the ball moves out over the course, okay, this one I would say is a very standard question for most of us. Okay, you'll find that the potential energy and the kinetic energy actually changes. Okay, so at the highest position, at the highest point, okay, you will still be having potential energy, you will still be having kinetic energy. Okay, so these are the what are the questions that what are the energy that possessed by the object itself. Okay, by height, and also because of motion, the ball is still moving, so there will definitely be kinetic energy. Now, what happened now is I have the same impact, I have the same angle impact, I have the same forces, but now I only do the experiment on moon. Okay, so moon is the only changes that I make on moon. Let's see, on moon, and same thing for moon. Okay, the gravitational attraction, the gravity, okay, will actually be the gravitational field strength will actually be smaller. Okay, this one is what we need students to know. The gravity field strength will actually be smaller. And because the gravitational field strength is actually smaller, you'll find that, okay, when I hit the ball at the same time, okay, the pull from the Earth is actually, the pull from the moon is actually smaller as compared to Earth. So as a result, the object will actually fly a further distance, both in terms of vertical distance, fly a higher height. Okay, it will fly a further also. The range of the ball will also be further a bit. Okay, so that's why we mean by horizontal and vertical distance both increases. Okay, so I would say it's a straightforward question for question 5. Okay, I would say it's a safety net question for students. Okay, so students for this, let's see how many marks. Okay, for this 2, 3, 4, 5. Okay, 4, 5 for this 5 marks or 6 marks. Okay, you should be looking at around 4 marks or 6 marks. Okay, full marks. Okay, you shouldn't be getting anything less than 4 marks for a safety net question. Okay, explain in terms of molecule, the kinetic model of matter, okay, the molecular structure of gas. Why is it able to compress but not liquid? It's a very common question. Why? Because gas being further apart, they will intermolecular bonds. Okay, and because they are further apart, they are actually already known that there are spaces between them. Spaces between a gas molecule. But if you compare to solid and liquid, because of the bonds, intermolecular bonds is very, very high, where you'll find that the distance between the objects, the molecules are actually negligible or actually very, very small. And thus, because of the small space, I will not be able to compress all the molecules together. And as a result, okay, the molecule will not be able to be compressed. The matter will not be able to compress, or the object will not be able to be compressed. And this is one of the reasons why liquid and solid is incompressible. Okay, because of the space in between them. Okay, so this is one of the key characteristics here that we have. Now, insulated filled with water and left open at room temperature. So what water, I don't know, but I know there's a room temperature. The volume of the water gradually decreases. Volume of thing gradually decreases, and the temperature of thing fall below the temperature. The temperature of water fall below the room temperature. What does this mean? What does this imply? This implies there is a certain amount of cooling effect, because the question actually fall below the room temperature. So which means there will be a certain point of cooling effect. And cooling effect, when we talk about the volume of water, we only look at one thing, which is evaporation. Okay, so in terms of molecule, how does the temperature decreases? And because we know it's evaporation, so we will know we just need basically the question asking how does evaporation work. Okay, so you have to let the marker know evaporation. Remember, evaporation is look at kinetic energy. It's not about although there's a change in matter, but the change in matter come about because of the kinetic energy. The molecule at the surface is actually vigorously or activated, or what we call is actually moving at a very fast rate. Okay, as a result, the molecule at the surface tend to break their bonds, intermolecular bonds, and actually leave the liquid surface, okay, to become gas. Okay, so what we need students to tell the marker is to tell us that they are more energetic water molecules. Okay, and what they did, the keyword is actually to evaporate. The keyword is actually evaporate or actually leave the contact surface or leave the surfaces. And what happened to the cooling effect? There is a cooling component here. So there is a cooling component here. So that you need to explain how the cooling component is brought about by the evaporation. Okay, and the main reason for that is because when I leave, okay, when the molecule leave, the molecule, those who left the surfaces are those with high kinetic energy. Kinetic energy is always packed with temperature. So what happened is when the faster and more energetic molecule actually left or evaporated, what is left behind is what we call the less energetic one, the energy, the molecule with the lesser energy. And because the molecule has a lesser kinetic energy, the temperature of the object or the substance, the container, will actually be reduced. So this is what we mean by your cooling effect. Okay, so this is what the answer for this actually revolve around the students explaining how does evaporation works. So you need to know the facts, you need to know what a keywords given in the question before you can answer this this particular question, question 6. Now for question 7, question 7 is a light question, okay, especially deal with refractive index. So it's more like a refraction question. Now for a refraction question, especially refractive index, okay, 1.5, two things when we talk about refractive index, okay, you need to know the definition for refractive index. The other component we look at is actually the formula for refractive index. The formula, there's actually two of them. There's no ES here. Okay, so the formula, shouldn't have to remember the two formula for refractive index. First is in terms of trigonometry, sine angle in the less than medium, okay, divided by this angle in the dense medium. Okay, the ratio of the two angles will give you the refractive index of the medium. Likewise, there's a second formula. The second formula here is dealing with refractive index, but we look at refractive index in terms of the speed, the ratio of the speed of the object, the light ray. So we have the speed of the light ray in vacuum, okay, versus the speed of the light ray in the medium. Okay, so in terms of refractive index, there are actually two formulas. So it's in terms of the angles, the trigonometry, right, or it's in terms of the ratio of the speed. So these two formulas are essential formulas to calculate this to calculate refractive index. So as a student, I will actually want to make sure that I actually know these two formulas before I go into the exam or before I attempt any physics assessment. Okay. And true enough, okay, the question at part B actually asks for the speed of light, okay, in the gas. Okay, speed of light in the gases, in the glass, sorry, not gas, in the glass. Okay, so given that the refractive index is 1.5, so speed of the vacuum is one of the constants that we expect students to remember. Okay, so there are two constants that we expect students to know. Is firstly the constant that gravitational field strength is 10 Newton per kg. The other constant that we expect students to actually know and we will not give is actually the speed of light in vacuum, or speed of transverse wave. Okay, if it is 3 times 10 power 8. So these two numbers, students will have to take note that you have to know this formula, know this value. So once you are okay with this number, you proceed on with the formula. Okay, and you'll be able to calculate the speed V. Okay, and your answer will be 2.0 times 10 power 8, okay, meter per second. So it will be like easily done. But take note, for you to answer this question, for you to tackle this question, the only thing that you need to do, is you must know the formula for the refractive index, especially these two formula. Okay, because if not, there's no way you can actually derive the answer. Now, the part B is lens drawing. Okay, focal length of 4 cm. Okay, so remember when we ask for definition, nowadays we usually won't ask like, please define focal length. Okay, the distance between the principal axis. Okay, what we want to do is we actually ask you to define like what we have asked, and we actually want to bring your definition in context with the question. So it's 4 cm here. Focal length is around 4 cm. So the definition for focal length is actually the distance between the principal axis from the optical center to the principal focus. So what we require students to do is, other than listing the definition, you have to bring the context 4 cm inside. So usually I'll ask students to say, after I give the definition, try to bring it in terms of to the context. Okay, and the distance is actually 4 cm. Okay, so I will need to use the 4 cm. I will need to use it in my answer, and I also need to define focal length. So when I combine these two, I actually require you to give me a definition of focal length with respect to the number that is given in the question, which is 4 cm. Okay, to draw reference or draw relationship with the question. So this is what we mean by answering the question, not just define. Okay, define with context. Okay, then after that, based on the question, okay, the question given, okay, is a what I call it? It's a object near to the focal length. Okay, the ray diagram such that the object height 2 cm, space on the left, okay, form a virtual image that's twice the height of the object. So given is twice the height. So based on the question, if you look at the ray drawing diagram, I have to actually, this is the object. I will know where the image is. Okay, the image is actually here. How do I know the image is here? Because the image is actually twice the height, okay, of the object. So after that, what you do, same thing as what you do in all ray diagram, you always draw ray 1 first. Okay, the ray that passes through the optical center, which is this. You remember to put your arrow here. Okay, then after that, you proceed on to draw your ray 2 and ray 3 here. So I will not, for this, I will not draw too much because it's quite a standard approach or standard question here. Okay, if you need to know how to draw the ray diagram again, okay, please refer to your chapter 10 or chapter 12, or chapter 10, okay, of a light worksheet of your light textbook. For ray drawing diagram, I actually have a video on it, so you might want to refer to the particular video for ray drawing diagrams. Okay, and of course, other than knowing all the ray diagram or the ray drawings, okay, one of the things that we always remind students not to make, okay, one of the careless mistake not make is actually to draw the correct image representation. For example, in this case, you look at this. This is a solid line, but the question asks for a virtual line. Okay, virtual image, it has to be represented by a solid, by a dotted line. So the image is actually a virtual image, so it has to be a dotted line, not a solid line. Okay, so the representation of the image is actually important. Okay, how if we the convention is we have is for image we use a solid line to represent real image. For virtual image, we actually use dotted line. So the representation of the ray, you have to be careful. Okay, so the ray and the image has to be careful because different type of rays or line actually represent different image itself. Okay, then after that, same thing. What we have done, what has to be done to the object such that a real image is actually twice the size that's produced by the lens. Okay, now I want a real image twice the size. Okay, for a real image, if you look at your if you have a ray drawing diagram on page, textbook should be page 198. Okay, you have 6 ray drawing diagrams, 6 of them. Okay, you have 6 of them, and you find that there's one particular location on the ray diagram that actually give you the image that's twice the size. Okay, what we call a magnified image. Okay, for a magnified image, and it has to be real. Magnified image, there's only, for magnified only, there's 2 images, there's 2 possible locations. One is what we call the question above, magnified, but it's virtual. The other position that we have is actually magnified and real. What the question asks for real. So for that particular location, the object has to be between F and 2F. For object between F and 2F, the image that you definitely get will be actually magnified and you'll be real. Okay, how do I know about this? It's actually, I actually make reference to the 6 diagram that's given to you in the textbook. So this is where I always tell students that to actually know the 6 diagram, know how to draw them, know how to see them, and actually know their users. Okay, not just knowing one of them. You need to know all the 6 of them. You need to know how to draw, how to use, and characteristic among for the 6 diagrams. Okay, and with that, you should be able to answer this question quite easily. Electric field, question 8. Electric field is definition, so I will not do too much. Okay. 8.1 talk about positive pair charge or opposite charge. Okay. So draw the electric field of the 8.1. For 8.1 is just opposite pair. The opposite is a electric field for horizontal plate. Horizontal plate, if you look at the electric field, okay, electric field is always from plus to minus, so it will be straight line. Okay. So the direction will be plus to minus. Okay, so this is where the electric field is. But take note, electric field for plate, for horizontal plate, okay, there is these 2 rays, the first and the side, we have to be careful, it's not straight. First and the last positive, the charges will have to be curved because it's under the influence, is being affected by the electric field on Earth. So the first and last electric field is always has to be a bit of curvy. Okay, but for the rest of the electric field in the center, okay, it has to be straight. Okay, because the impact between the two, the attraction force between the two plates is actually strongest in the center. Okay, so, but for the rest, for the side, especially the first and last line, remember the electric field has to be curved a bit because it's under the influence of Earth electric field. Okay, then after that, based on the questions, I have a stream of negative charges, droplet, as they project into the electric field from the left. Negative charge. What does it, what's the impact? Okay, what's the impact? If it's negative charge, okay, this is where your electrostatic come in, unlike charge attracts, like charge repel. So what we do is, if I have the object, so let me erase a bit. So you have the electric field here. Sorry, if I have a negative charge object, oil droplet here, you'll find that this is negative, this is positive, negative, they will be attracted. So which means your oil will actually be pushed upwards because of the attraction. And similarly, because this is negative charge now, this is negative charge, the plate is negative. So this is what we call light charge repel. So you'll find that the bottom plate will actually push the oil drop, okay, towards the top. So you'll find that the positive plate versus the drop, the oil droplet, you'll be pulling it up. The negative plate versus the negative oil droplet, you'll be pushing up. So you find that these two forces actually push upwards. So eventually, I will know that the oil stream will proceed as it move along the electric horizontal plate. He will actually move nearer to the positive plate. Okay, or what we call it will be deflected upwards. Okay, because of the attraction between the oil drop and the positive plate, because why? Unlike charge attracts. And it also move up because the negative charge versus the negative plate at the bottom is also, there's also a repulsion force. So all the two directions of the force actually point upwards. So definitely the oil drop will actually be deflected upwards. Okay. Now, in the last experiment in 8.2, I have a negative charge. So it's negative charge. Okay, so this is negative charge. Okay. But now in this case, right, even though the plate is opposite, the top plate and bottom plate still remain the same, plus and negative opposite charge, the oil drop do not actually move up like what we see in your 8.1. Okay, so what we have now is this. You have when this is negative charge, I have attraction force. Okay, because positive plate and negative plate, okay, unlike charges, they will attract. Okay, and similarly now, because I am a negative charge with respect to the bottom plate, okay, I have a light charge repel. So this is my repulsion force. So you find that there is actually two forces acting upwards. And same as 8.1, the negative oil drop should actually move up because the two forces actually, the electrostatic forces actually point upwards, both of them. Okay, but yet the question says it doesn't move anything. So how does it work? Okay, the difference between the two of them is that it could be, okay, there is one force that's not accounted for. And that force is actually the force that will actually counteract all the two upward forces. And as a result, it will actually remain in that position. And what is the forces that we have forgot to take note of it is actually the weight of the droplet. So the weight of the oil drop. Okay, so if what happened here is if the weight of the oil drop, okay, is as big as the attraction force and the repulsion force, if it's as big as the total two of them, okay, the two upward force is as big as the two of them, you'll find that the downward force and the upward force will actually be balanced. Okay, so if the weight and the total force is the same, okay, and I know that the weight actually point downward, so it will be a downward force. So what we have is actually the upwards force and the downward force actually balance off. And because it's balanced, you'll find that the net force on the oil drip will actually be 0. So even though there's a 3 force on the oil drip, but because the weight is as big as the sum of repulsion and attraction force, okay, you'll find that eventually the oil drip will still be floating in the middle, okay, because it will be stationary. 0 meter per second square, it will be stationary, okay, because the oil drop is balanced by the repulsion and attraction force. Okay, so and as a result, the oil drip actually remains in the middle, okay, not moving up and not moving down, because the oil drop happens to be maybe of the correct size. It happens to be a size that is actually twice the sum of is equivalent to the sum of the repulsion and attraction force. Okay, so this is what happened to the electrostatic forces. Okay, so this is where we actually actively uses light charge attract, light charge repel, and light charge attracts, and also we may use of other forces like your weight itself to actually give a meaning to the analysis for electrostatic forces. Now for question 9 is an electric circuit. Okay, so you have four cells, okay, 1.5 each. So it's literally EMF of total here would be 6 volts. Okay, and it's in series. 3 ohm and 1 ohm is in series. Okay, and the two of them will actually be in parallel with your 6 ohm. So combined resistance, I will actually sum up the resistance, the series circuit first. Then after that, the resultant sum of the series is actually parallel to the 6 ohm. So it will be a series first. I will sum the circuit by series first, followed by parallel. Okay, so if you sum the resistance correctly, the answer will be 2.4 ohms. Okay, so I will not dwell too much on the working. Okay, this one is, I would say, is the basic that all students must know. Okay, it has to know. Power dissipated by all the resistors. Okay. Now, power dissipated by all the resistors, there are two ways of looking at it. Okay, so there's two ways of looking at it. So if I want to know the power of the resistor, so one of the easiest way or one of the possible way I'm looking at is actually to come up with the power of one resistor. Then after what I do is I will multiply it by 3. Okay, because if I know all the 3 resistors, I would know that if I can sum out the power of all the 3 resistors, I will actually have the total resistance, total power dissipated by the resistor, because energy can be added up together. So I will look at the power by the 3 ohm, 1 ohm, and 6 ohm respectively. Then I'll get the power dissipated by all the resistors. The other way of doing it is actually calculate the power of, I want the power of 3 resistors, but I can actually calculate it by looking at the total forces, the total EMF and the total current produced. So actually, the power by the 3 resistor is actually equivalent to the power given out by the EMF. Okay, so if I look at the power of EMF, whatever power I need by all the 3 resistors, it has actually come from the battery itself. So the two numbers are actually the same. Energy is conserved. Okay, so if I look at the energy power of the battery itself, power of the battery, I will use P equal IV. No, I will not use that, because IV, I don't have current. But what I do now is I actually can use V squared over R. But if I know V squared over R, why I want to use V squared over R? Because in this question, I know the total EMF is actually 6 volts. And I know the total resistance is actually 2.4. So I actually got this number already. So I will not want to use P or IV because I don't have current. So I need to spend a working to calculate current. But if I don't want to use current, I can use V squared over R, because I'm given the form. The V is given is 6 ohm, 6 volts. The V is the power, the EMF is given is 6 volts. 6 volts. And I know the total resistance is 2.4 ohm. And after that, I will know the formula. I will have the energy or the power uses by all the 3 resistors. Okay, and the answer will be 15 watts. Okay, then part B, define current. Define current, standard definition. Rate of flow of charges. Calculate the current across 3 ohm resistor. 3 ohm resistor is here. Is the current in the 3 ohm resistor. This is the current that I want. And this is the current also going through the 1 ohm resistor. Okay, so fair enough. If I want to calculate the current flowing through 3 ohm resistor, I can actually look at this branch. But I know the total of this branch, the voltage, it has to be 6 volts because they are in parallel with the battery. So if I use the formula V equal IR, current is voltage, potential difference divided by resistance. Okay. So what I do now is this. I can actually calculate the current flowing through this branch. Because if I know the current flowing through entire branch, I also know the current flowing through the 3 ohm. I also know the current flowing through the 1 ohm. Because they are in series, current remains the same. Okay, so that's why I use 4 ohm. 4 ohm here represent the total resistance in the branch. So what I'm doing is I'm looking at it as a big picture whereby I look at the voltage is the EMF, the resistance is the total, and then from there I will know the current produced by the current flowing in the cable, which is 1.5. Then after that, state the combined EMF. Okay, if one of the cell is in reverse order, take note if it's one of the cell is in reverse order. Okay, if it's reverse order, so let's say if I have reverse order, here need to take note if I have one cell that is reverse order, so that's let's say this cell. Okay, it doesn't mean I just minus 1.5. Okay, if it's one cell that is reverse order, what happens is that the neighboring cell will also be negated in the sense that if I have a negative 1.5, this negative 1.5 will affect the neighboring cell. They will actually cancel each other, effectively making these two cells into what we call behave like a wire. Okay, like ideal wire. Okay, so effectively, if I have one cell that is, I have a cell that is reversed in order, what actually happens is that the neighboring cell will also be affected, and thus 2 cells will be cancelled out. So 2 cells will be cancelled out, and I will left with the remaining 2, which is why I know the EMF is 3 volts. So take note, the only thing I need to highlight is when I have cell in reverse condition, one cell reverse condition, the neighboring cell automatically will be affected one. Okay, so that's why the 2, so if I have one cell is in reverse order, it's effectively telling the marker to say that I actually, telling the students to say that I actually have 2 cells rendered, 2 cells, okay, not working properly, not working. And they are, when I say not working, they actually behave like a cable. Okay, so take note of this, okay, of this reverse cell. It's something that we don't actually see often. Section B, okay, remember section B, the marker will require students to choose 2 questions. Okay, remember, choose the best 2 questions. Okay, it need not be the first question. Don't just look at the first question and you just do straight away. Okay, remember at section B, remember to read all the 3 questions first. After that, attempt the 2 questions that you have the most confident in getting the most result, or getting the better grades, or getting the most mark out of it. Okay, don't just choose question A because I like I'm good at non-tuner wave. I'm good at sound wave. Maybe because you might be good at sound wave, but the question may not entitle because this question may be explanation question, and maybe you are not strong at explanation question. You're stronger at the calculations. So in this case, although sound is your favorite topic, it may not be the question that you want to choose because it may not be the question that will have the highest mark. So in section B, whereby you choose the 2 questions, it's important to choose the correct 3 questions. Choose the 2 questions that will give you the most marks. Okay, so that you can evaluate section B to your overall grades. Question 10, okay, is on the sound question. Okay, vacuum pump. Okay, battery operated vacuum pump I would say is a classic setup. Okay, whereby look at whenever we deal with this type of question, we actually look at the sound need a medium to pass through. Okay, so this is that's what the question is trying to tell you. Okay, and the speed of the sound slowly increase. Okay, now when the air passes through, okay, and through the glass, okay, sound travel through the glass into the jug. But now take note is what happened is in this case is removing the air. A vacuum pump is remove the air from the bell jar. How the speed of the sound changes when it passes through the air to glass. So now let's say we are looking at it, I have not taken out any air yet. So what happens is when I look from air to glass, remember speed of sound, okay, it's actually highest in solid. Highest in solid, slowest in gas. So when I go from air to glass, okay, effectively I'm actually seeing an increase in the speed of sound. Okay, so that's what we mean by the speed of sound. So now as I move through the sound, when the sound moves through, okay, what are the things that remains the same? What are the things that remain that will change? Okay, always remember the speed of sound. For talk about speed, frequency is like the IC or the identity of the sound itself. So usually when we talk about passes through different medium, okay, the frequency of the object actually remains unchanged. How do I know it remains unchanged? Because frequency is like the identity of the wave itself. So when I travel through different medium, I am still that particular sound. I am still that particular of that particular frequency. Even though I'm at different medium, but I am still that sound. I am still classified by my frequency. So that's why we talk about air traveling through different places, sound traveling through different medium. One thing that remains unchanged every time is always what we call the frequency. Okay, so your frequency is always unchanged. Okay, but take note, because when I travel through the medium, the speed of the object actually changes. And what actually causes the changes is actually the change in the wavelength of the object, of the sound. Okay, so when the wavelength of the sound changes, the sound of the wave actually changes. Okay, so these are the few factors that you have to take note. Okay, frequency of the sound actually most of the time it actually remain constant. Okay, then after that, followed by the wavelength. The wavelength changes when I go through from different medium. After the next part is when what happened to the sound when the air is being removed. Okay, removed from the bell jar. Okay, so take note of the question. The question says the sound is being removed. Okay, so what will happen? Or okay, take note, the sound will not disappear straight away. As this air is being removed, it is a process. It takes some time. So while the air is being pumped up, the sound actually becomes softer and softer because there's air already. Okay, the sound, the bell is still ringing at the same magnitude, it's still ringing at the same intensity. But why the sound actually, when we heard, is actually getting softer and softer, is because the amount of air inside the bottle is actually getting lesser and lesser. So it's getting harder to transfer to conduct the air out of the to your ear to hear the voice. So that's why we hear it in terms of getting softer and softer. Okay, and eventually, when all the air are pumped up, the sound will be unheard. There will not be any sound. Okay, but remember at this time, although there's no sound, but the bell is still ringing. It's just that we cannot hear because there's a vacuum inside. When sound need a medium to propagate. Okay, that's one of the main reasons that we need. Okay, or what we call sound cannot travel through medium. Cannot through vacuum. Okay, so take note of the properties that we are looking at and take note of the explanations. Then after that, for vertical rope, B is another context really. So B will be a vertical rope being swinging up and down. So you have a wave itself, you have a rope wave, okay, and take note of the property. Okay, you have amplitude, all this amplitude, wavelength. Okay, so take note when we look at amplitude, it's always from the horizontal position all the way up to the crest. Okay, so this is what we call your amplitude. Okay. So when we talk about wavelength, it's always one cycle. Wavelength is always one cycle. So let's say if I take from here, it's a cosine curve. So this is one amplitude. So this is one wavelength. This is amplitude. Okay, so take note of the measurements for amplitude and wavelength. Don't just take the number 10 and 18 because why the question give you, or because the question give me 10 and 18, I will have to take it that the amplitude is 10, the wavelength is 18. No, it doesn't work this way. Where sometimes the question tends to like want to trick you. For example, in this case, 10 is actually not the amplitude. 10 is actually twice the amplitude because amplitude is measured from the middle, the equilibrium, to the crest or equivalent to the trough. 10 meter here is actually what we call the tip crest peak to trough location. Okay, so it's actually amplitude here. I would be safe to say it's actually 5 cm. Okay, half of the distance given. Okay. Definition of wavefront. Okay, just take note of it. And after that, it's quite a common thing: transverse or longitudinal wave, or AKA definition of transverse and longitudinal wave. So these two are what we call the classic questions that we have for sound. Most of the time, you always see this being asked quite frequently. Okay, so take note of the answers. Okay, it's actually quite a classic question of definition. The period of the wave. Okay, period of the wave. Okay, given period of wave is time for one cycle. Time for one cycle or one wave. Okay, given the question, there's 10 cycles within 5 seconds. So I want one cycle. So one cycle automatically will be 0.5 seconds. Okay, remember the definition of period is actually one cycle, time for one cycle. Okay, and with Period of the wave, I also know that the frequency will be 1 over t, which is 1 over 0.5, which happens to be 2 Hertz. Okay, so speed of the wave, I will need to use the formula V equal to F lambda. Okay, lambda here, remember, I'm given 18 cm, but this is not 18 cm. This is one wavelength, half a wavelength. So effectively, this 18 cm, what the question is trying to trick you is, this is actually giving you is 1.5 lambda. It's actually 18 cm. Okay, so 1 lambda, okay, will be 12 cm. Okay, because 1.5 is 18 cm, so 1 lambda will be 12 cm. Okay, or what we call 12 meter, 0.12 meter. So with the number, I know the frequency is 2 Hertz. I know the frequency is 2 Hertz. I know the lambda is 12 cm. So with these two information, I will be able to calculate the speed of the wave using the classic wave formula V equal F lambda. Okay, same thing. Once I have the formula, I will get. Once I plug in the variable inside the equation, I will be able to get the answer straight away. Now, for part 5, okay, part 5, frequency increase to 5 Hertz. Okay, state the effect on this increase in frequency. Remember what I mentioned before, wave has certain things, V equal F lambda. Okay, now the question said the frequency actually changes. So you check what happened. So you check what are the things that have changed. You look at the question, the context of the question said the frequency has increased, but the wave medium is still vibrating in air, is still vibrating in the same environment. So effectively, I can say that because I'm in the same environment, okay, the speed actually remains constant. What actually will change is that the wavelength of the frequency will actually changes. Okay, so example, if my frequency increases, the wavelength of my wave will actually decrease. Why will it decrease? Because okay, the frequency, the speed of the object in the medium has to remain constant, because the speed of the wave, okay, actually depends on the medium itself. Okay, so if I'm giving a water wave, the speed will be different as compared to the same wave water wave, the wave in the air. Okay, so that's why the changes in the speed, changes in the frequency, all this you have to remember carefully. Okay, so take note of what we mean by the wave formula. It is effectively V equal F lambda, actually help us to actually calculate all the variable. And indirectly, the second important thing about wave formula, not just in calculation, it actually help us to predict what will change, which factor will change when certain condition of the sound or the wave itself actually changes. Okay, so take note of the formulas to know them and see what are the context that is being used. Question 11 is a classic example of pressure and volume, all these things. Okay, so part A, 1 and 2, I will not dwell too much. It's a classic example of force over area. So far, I will not have, my students have no problem with it. So I will just leave the answer here for you to take a look. Okay, if you have problem for this question, just give me type it in the comment bar below, and I will come back to it. Okay, whenever you need. Okay, so for part B now is when the force is 35 Newton is pushed to the right here. Okay. Now, then after that, what happened? Okay, the question asked for definition for center of gravity. Yeah, of course, is a common definition. But take note, center of gravity. Okay, one of the keywords that we always ask students to always remember is the word appear. Okay, center of gravity is I would say a pseudo point that we connect with. So it always you need to use the word like appear, because it doesn't actually exist. Okay. Now draw the weight of the object on the slab. Okay, it's quite straightforward. So the force will be here. Okay, take note of where you draw the weight. It has to be the CG. And the CG, it has to be in the middle of everything. Okay, it has to be in the middle of the object. Okay, whether it's horizontal or vertical axis, CG is always in the middle. Okay. Then after that, calculate the moment of the 35 Newton about X. So where is X? So X is the pivot here. Okay, so 35 Newton. Okay, this is the force. The perpendicular distance between the force and the pivot will be here. So it will be 0.6 will be the perpendicular distance. I will have the force, which is 35. And you'll know that the moments I'm looking at, it actually will be a clockwise moment. So you substitute the formula inside, and you get the answer straight away at 2.1 Newton meter. Okay, take note of the common booby track, 60 cm, okay, 0.6 meter, okay. Take note of the formula, okay. Yeah, about X. Okay, I think I made a mistake here. Maybe it should be not 0.6, it should be 0.60. Okay, my mistake, my mistake. Okay, so take note of this, this should be 0.60. So if you look at the question, it should be 35 times 0.6. Okay, answer should be 21 Newton meter. It should be 21 Newton meter. Okay, why? Because the perpendicular distance is 0.6. It's not cm, it's not meter. Yeah, after that, point X, the moment of weight. That the trick here is the weight of the weight, the moment by the weight. Weight of the moment, weight is here. The perpendicular distance between the force and the pivot is actually here only. This is the perpendicular distance. So it actually is 0.15. Okay, so the perpendicular distance is 0.15 meter. So the moments by the force is actually 0.15. Okay, 18. So this will be 2.7. Okay, then after that, okay, you move on. So the calculation, I would say, is quite straightforward. Plug the value in, shouldn't be any difficult. Okay, then after that, the question asks for friction force. Remember, friction, it has to be at the surfaces. Okay, the location is important. Okay, so if friction is pointing to the right, okay, so if you look at it in terms of friction, it has to be going to the left. Okay, you have drawn between the surfaces that's in contact, or we call the contact surfaces, contact area. Okay, so take note of the direction and the location. Okay. Then after that, explain what happened to the slab as the horizontal force Y is gradually increased from 35 Newton. Okay, horizontal Y, okay, horizontal force Y is increasing. Okay, this will mean that if you look at it in terms of moments, okay, in terms of moment, you'll find that the clockwise moment is actually increasing. Okay, so what happened is that, what's the result of it? Because the anti-clockwise is actually increasing. Okay, it's much bigger. Because 35 Newton is the only one that's increasing, the weight remain constant, the friction remain constant. Okay, so when the weight remain constant, okay, when the weight remain constant, or what we say, the clockwise moment by the weight actually remain constant. Okay, this clockwise is by the weight of the object, it remain constant. But what happens is my anti-clockwise moment actually increases. Okay, that's because of my 35 Newton, it keep increasing. So my anti-clockwise moment will actually be affected. It will be get bigger and bigger and bigger. And as a result, the object will be tilted. Okay, and thus the block will be tilted. Okay. Yeah, or you'll be lifted off the ground, or the slab will be, or the block will be rotated clockwise. Okay, so take note of the answer here. Okay, so take note of the rotation. So in this case, the box, okay, 35 Newton increases. Okay, so within the box eventually will be tilted this way. The box will be tilted this way. This is 35 Newton. Okay, so the box eventually will be tilted at X. Okay, so the box will actually rotate. Okay, anti-clockwise. Will rotate clockwise. Okay, so take note of this. Now for question 12, okay, question 12, electric heater. Okay, electric heater, the specification given, 1.2 volts. Okay, so there's two power rating here. Take note, there's two power rating. Okay, 1.2 kilowatts and 2.4 kilowatts. Okay, rating will be 220 hertz, 50 hertz, 220 volts, 50 hertz. Okay, definition, I will not dwell too much. Okay, now which of the component has to be earth? Okay, this earth, remember, earth has to be where? The casing. Okay, but don't just write casing, you have to write the metal part of the casing. Okay, the metal casing, okay, it has to be earth. The metal casing has to be earth, or the earth wire has to be connected to the metal casing. So important word is not just the word casing, is to actually highlight to the marker as it has to be on the metal part of the casing, or if not, it's on the whole metallic casing. Okay. Now, state what happened to hazard if the heater is not earth. Okay, what happens when it's not earth? Okay, when it's not earth, okay, you will have what happened when it's not earth? It will mean that when there's a fault occur, and what fault pertaining to earth wire is when the live wire actually touch the metal casing. Okay, when the live wire touches the metal casing, and what happened? And the casing become live. Okay, so when the casing become live and a person touch it, it will cause electrocution. Okay, and that's why it's actually important for earth wire to be present, okay, especially when you have items with metallic casing. Okay, because when the live wire touches the metal casing, which is the keywords, okay, the casing will be live, casing will be at the high potential, and if it's not earth, electrocution will occur. Okay, so this is what happened. The importance of earth wire is to prevent electrocution due to where your earth wire touching the earth wire touching the metal casing. Okay, now I have two heater here. Okay, the question of two heater with two switches, so that either one of them will be on. Okay, in the space below, and I have to connect it to the to the main supply. Okay, remember it's two switches are individual switch. So if you connect, okay, take note it has to be connected here, connected, and take note the switch has to be in the live cable. The switch has to be in the live cable. Okay, and after that, the two cable must go back to the neutral. Okay, and take note, based on the question, it has to be connected in parallel. Okay, because the component here we're talking about, it has to be individual switch. The idea of individual switch is I can actually switch on any one of them. And to do that, it means it has to mean that the arrangement has to be a parallel arrangement. Okay, so if I want to on the top, one heater, I will if I want to switch on the top heater, I'll just switch on the switch that's nearest to it. If I want to switch on the heater on the bottom side, I will just activate the switch at the bottom side. So I can actually be switched on individually. So switch on individual switch, aka means parallel arrangements. Okay, and parallel arrangement, take note the switch has to be at the parallel side. Okay, at the parallel wire there, nearer to the parallel wire. Okay, so take note of the arrangement. Now, tripping plug, okay, is another safety device. Okay, what happened to the safety? What's the beauty of the tripping plug is because there's a fuse inside. It allows us to hold the fuse inside. And what happened when what will happen when the fuse, or what will happen when it cause the fuse to blow? Okay, remember. Now, when the live wire touches the metal casing, okay, that's one possible scenario. When the live wire touches the metal casing, or what we call the live wire is activated. Okay, so when the current flow from the live wire to the earth cable here. Okay, so the earth cable here, so this is what we call earth fault. So when the current flow through the earth wire, okay, the current is high enough, okay, and the fuse will blow. That's one of the possible reasons. The other reason that we have for fuse to be activated is when there is a short circuit, when the live cable and the neutral wire actually shorted itself. So maybe it could be somebody drop a piece of wire, or maybe the live wire actually is being maybe a fork, a metal conductor actually placed between the live wire and the neutral cable, causes it to be short circuited. And so when it's short circuited, the current will also be high enough to flow. Okay, so when the current high enough to flow, what happened is the fuse will melt. Okay, to protect the appliances and the user. Okay, so take note of the cases whereby you have fuse being activated, when fuse is activated, when earth cable is activated, when circuit breaker is activated. So all these safety precautions, you need to know how it works, okay, individually, and how it works together. Okay, so what happens when I have an earth cable being connected to a fuse, all these things. Okay, so you must know when it happens. After that, calculate the maximum power in kilowatt hour. Here, I would say is a standard formula. Just take note of the common trick. Okay, it has to be in kilowatt. Power has to be in kilowatt. Time has to be in hour. So 45 minutes, you have to make sure you change it to 3/4 hour, and I've used it for 30 days. The question here, I'm looking for a maximum power. So maximum power I'm looking for is I have to use the bigger number, which is 2.4 kilowatt. Okay, if I'm minimum, maybe I'm looking at 1.2 kilowatt. So if I'm looking for maximum, it has to be 2.4 kilowatt. Oh, see. Okay, 2.4 kilowatt. Timing will be 3/4 times 30 days. So this will be the total amount of the total energy used by the heater itself. Okay, I would say it's a fairly simple question here. So just take note. So if I were the student on that day, I would definitely choose this question as one of my 2 questions. Okay, so I have 2 questions. I have done through the paper 2. So if you ask me for section B, which are the 3 of the 3 questions, which one will I actually use? Which one will I actually choose? I would definitely choose the last question, question 12, because I would say there's not much trick, not much booby trap in that question 12. Okay, and I am very confident that I will get the most mark for question 12. Between 10 and 11, question 10 and 11, I would say that if I'm not confident about sound, okay, like what happened to the frequency, what happened to the wave when the frequency changes, I may want to skip this question first. I may want to look at question 11 first. Okay, but I'm not saying I will do question 10, but I will just look at question 11 first. So I'll look at question 11, see what are the possible questions that I will be getting correct. So if you look at question 11, I would say that I'm more confident that I am more confident in me getting question part A correct completely. B1, B2, B3, I'm actually quite confident to get B1, I say part A1, A2 correct, completely correct. I'm also confident that part 1 is correct because I've done my job in knowing the definition. I also know how to draw the weight. And I am very confident I'm able to calculate the moment. So I'm actually able to get, I would say, 3/4 of the question. What I'm actually quite shaky about, or quite not confident about the question is maybe B part 4, whereby what happened to the slab when horizontal Y. But if I look at it, part B, part 4 is only like a 3-mark question. So out of 10 marks, I'm still confident to get 7. So if you look at the number of marks I can achieve for question 10 and question 11, I would say that question 11, I'm fairly confident that I will be able to secure the 7 mark completely. Okay, for question 10, maybe I will be able to secure maybe like 5 marks. Very confidently, 5 marks confirmed. But question 11, I'm very confident that I can secure 7 marks minimum. So between 10 and 11, I will definitely choose 11. So the 2 chosen question I have is actually question 11 and 12, the last 2 questions. Okay, so true enough, okay, this is where the impact of your section B, whereby you're choosing the right question actually help you. Where section B, when you look at choosing the question, okay, you have to choose the question that give you the most marks, because section B, 10 marks each, the question is actually quite a heavy weightage. And if you've done it, if you handle it correctly, okay, section B will actually value add, okay, will allow you to push up your grades, okay, at least by 1 level. Okay, so if not, okay, this is where I end off for today. Okay, so for this paper, you have not done it. Okay, I repeat again, the file is in my Google Drive. Okay, you can actually get the file from there and actually can practice. Okay, if I make any mistakes in the questions, or if I have left out any things that you want me to explain further, okay, remember to just leave me a comments at the bottom below. Okay, so if not, okay, if you want to be notified or want to be updated with the other videos that I uploaded, it could be exam papers or it could be some debrief on certain topics, remember to subscribe to my channel, and after, remember to activate the bell icons, okay, so that you get notification whenever I upload it or whenever I conduct any live streaming activity. Okay, if not, okay, see you in the next paper. Bye bye.